Can you explain Turing complete, and is it necessary? No, it's not necessary. You can use DSLs that are Turing incomplete if desired, to run smart contracts or special purpose contracts. But Turing completeness is nice because you have a sense of genericism with your system. Now, most of these systems are quasi Turing complete because they're metered. So it almost is there, but not quite there. And basically, the idea is that you can express in your language, you have a sufficient level of expressiveness in your language to model pretty much any type of transaction that you'd like. Now, whether that transaction is cost effective or that transaction is useful for your context is completely contextual to the underlying virtual machine infrastructure that you're using and the computational model that you're using. But in general, it's desirable to have a Turing complete system because you have more flexibility with it. But there's a lot of pitfalls. Like, for example, you cannot get a proof that code will terminate. It's called the halting problem. So what you need to do is use a metering system so you run out of a resource for that. But then in introducing a metering system with your computations, you introduce a great degree of potential complexity in attack vectors, which is why Ethereum has to be retuned over and over again every hard fork, because there's always something that goes wrong. But if you're really interested in Alan Turing's original paper, where he actually uses it to show that the Einstein-Dunks problem is false, then I'd encourage you to read the book Annotated Turing from Charles Petzold. And he does a great job basically breaking down the preliminaries behind Turing's paper and then actually going through the entire paper paragraph by paragraph with annotations explaining what is a Turing machine and why does the proof do what it does. What Turing was trying to do, along with Alonzo Church and Kurt Gödel, and they all did. Church did lambda calculus, and Gödel used recursive functions for this, but they're all isomorphic approaches. But basically what Turing was trying to do was solve a problem that David Hilbert had presented. So basically, mathematics needs to have four properties for it to be a good system, or at least this was the belief at the turn of the 19th to 20th century. In the International Math Conference in 1900, this was like the big thing they were pushing with Bertrand Russell and Alfred North Whitehead and all these other logicians like Gottlob Frege and so forth. But basically the concept is that you first would like to have a system that is independent and consistent. So independent meaning that all the axioms of your system, so the things that you assume to be true without proving that they're true, those axioms basically are all necessary and they don't prove each other, meaning that one can be derived from a collection of others. And I mean, this is not obvious. Like Euclidean geometry, for a long time, people are curious if the parallel postulate was independent or it could be derived from other axioms. So people have spent quite a bit of time thinking about that, over 2,000 years. Turns out that it is. And then you would like consistency. So you don't want a situation where by assuming two things or more or n things to be true, that the system will be basically violating itself. So something would be both true or false or something because of axioms that you have in the system. Okay, so mathematics has the axioms that we constructed for set theory, our mathematicians constructed, are sound from the perspective that they're independent, we believe, and consistent. Where you run into some problems is completeness and decidability. So completeness is the property of saying, if I have some arbitrary statement that I'd like to derive the truth value of, we call this a WIF, a well-formed formula. So it's some proposition of logical connected things. Then you should be able to find a reduction to that, to the axioms of mathematics. So you should be able to say that that WIF is, you have enough information in math to prove it. Now, if your system doesn't have enough axioms, meaning there exist statements in the system that can't be proved within the system, it's called an incomplete system. Now, there was a very famous mathematician named Kurt Gödel, who as a graduate student actually studied this problem, and later in his career discovered through Gödel's incompleteness theorem that not only is math incomplete, it can never be made complete by the construction of the laws of mathematics. There's this inductive axiom requirement where you can always construct a statement outside of the system as a consequence of the prior axioms. that can't be proved with them. You'd always need to add another one, and then by adding it, you can construct another statement. And he uses all these clever ideas like Gödel encodings and so forth to do that. So that was pretty depressing. Like, hey, you can spend your life as a mathematician, but you're working within a fundamentally incomplete system. It's not true for all mathematical systems. Like Hilbert's formalization of geometry is complete. But then the last question is decidability. So let's say you could build a magic machine, and this is where computer science came from and what Turing was interested in, Church and Gödel were interested in. So you could build a magic machine that you can put in your well-formed formula, and out it would spit true, false, or undecidable, meaning you don't have enough information in the system to be able to prove it. So David Hilbert, who was the guy that really got all this rolling, was absolutely convinced that you could do that. And what Turing did as a graduate student, which was quite remarkable, is that he showed you couldn't do that in general. And he did it by constructing something called a Turing machine. But in the process of doing that, he basically constructed the foundations of modern computer science, which is another remarkable thing. Although at the time he wasn't fully aware of what he had done. And the other formulations of this also are alternative models of computation that are used, like lambda calculus is used with Haskell, for example. So there's a lot of magic there in these systems, and the people who studied that are called logicians. Kind of rhymes with magician, but it's called a logician, and set theorists. And there's been many, many famous logicians throughout the years, from Cantor and Gödel, and set theorists throughout the years, and most of them go crazy. Gödel went crazy. He starved to death because he thought people were poisoning his food. He was a paranoid schizophrenic. And Cantor also went crazy. So it's not good for your mental health to study these things, because you start thinking about things like the continuum hypothesis and so forth. Anyway, so if you're interested in that story, The Annotated Turing is a great story.